Chapter 6, Number 52. Driving in your car with a constant speed of v equals 22 meters per second, you encounter a bump in the road that has a circular cross-section as indicated in the figure. Given the radius of the bump, find the apparent weight of a 67 kilogram person in your car as you pass over the top of the bump. So, if the person's in your car, they've got to be tracking out the same circle as your car. So, what we'll have is we sort of draw a free body diagram. The person will just be a dot for us right now. The person is being pulled down by gravity, which we'll call F sub g as we usually do, and they're being supported in their seat by Fn. And from our stuff from last chapter, you should remember that in essence, their apparent weight is going to be Fn. How hard is the seat pushing against them? On level ground, it pushes, since there's no acceleration, Fn would equal Fg and would be their actual weight. But in this case, the person's going around a circle, and therefore they are accelerated. They're accelerated towards the center of the circle, and they're accelerated at the centripetal acceleration, which we can compute. So we know the centripetal acceleration will be v0 squared over r, or in this case, 22 meters per second quantity squared, over a radius of 52 meters, which gives us a centripetal acceleration of 9.308 meters per second square. I'm deliberately keeping far more sig figs than I should until the end of the problem because we don't want to round too early. All right, then from the diagram, we end up with a relatively easy collection of forces. We have that the sum of the forces in the y direction for this person is the normal force pointing upward and the weight pulling downward, and since its opposite is the normal force, one of them must be minus, and traditionally we'll take up as positive and over as positive. All right, and then we have from Newton's second law, we have that the sum of the forces in the y is the mass of the person times their acceleration, which is ac, but again we indicate it's against the direction of the axes, so it comes in as a minus. And then we just say, well, sigma fy has to be the same no matter who, so we end up with that Fn minus, and I'm going to change F sub g into m times g, and I'm going to say that has to equal m times a, which is minus ac downward. We're looking for Fn, so I'm now going to solve this by adding mg to both sides, and we get that the normal force the person suffers is their mass times g minus their mass times ac. Or really, we'd probably combine that. So we would have just their total mass times the difference between g and how much they're actually being accelerated downward. So we throw that in here and we find, let's see, the mass was 67 kilograms. We have 9.81 meters per second squared minus the 9.308 meters per second squared, and we end up with 33.634 newtons, which of course with appropriate sig figs becomes just 34 newtons.